This lesson is from Chapter 13 in Wiley, Acids and Bases. In this lesson we'll go over the Arrhenius definition of acids and bases, Bronsted-Lowry, strong and weak acids and bases, and consider water as an acid or a base. So what do you think of when you think of acid? Normally in the movies it's a vat of noxious liquid that people often get threatened to be dumped into. So what is it and why is it important? A definition is acid is an ionic compound that dissolves in water, but there are many ionic compounds. Acid is special. Let's consider some common acids. Sulfuric acid, nitric acid, hydrochloric acid, and acetic acid, the active ingredient in vinegar. These are all common acids. What they have all together is that they donate H+ ions into an aqueous solution. We know when an ionic substance dissolves that water molecules get between the positive and negative ions. Something solid like sodium chloride, the water molecules get in between. The ions are still there, they're just not next to each other in an ionic crystal like they were. The two special features about acid are that, number one, our solvent will always be water. There are other liquids that dissolve substances, but in this course, when we talk about acids and bases, our solvent will be water. The second feature of acids is they are ionic compounds that their cation, their positively charged ion, is H+. H+ is a very special ion. Why do we care? Many of the chemical reactions in our bodies depend on the amount of H+ ions. If that concentration is too high or too low, our bodies stop working correctly. So we are concerned about acids and how to measure them. We'll start with the Arrhenius definition of acid. He said that acids are substances that increase the H3O+ concentration in water. Well, before we were talking about H+. H+ is a hydrogen atom without its an electron, and that makes it a proton, a subatomic particle. In an aqueous, in a water solution, that proton does not exist by itself. It attaches to a water molecule. So a proton plus H2O gives us H3O+. That's also called a hydronium ion. So the proton's positive charge attracted to the negative side of the water molecule, the lone pairs. We already know that water is a polar molecule. This is not an actual chemical bond. And the H+ is not attracted only to a single water molecule. We have a network of this H+ surrounded by multiple water molecules. We could say H3O+, H5O2+, even H51O25+. There are many, many water molecules surrounding this H+. Here's a diagram. Here's what you need to take away from this. Some definitions will use H+, some will use H3O+. Remember that water is our solvent, so both terms will mean the same thing, and you may see them used interchangeably. So if you see H+ or you see H3O+, this is the positive ion that acids donate to solution. So back to the Arrhenius definition. According to Arrhenius, acids increase the concentration of H3O+, H+, in a solution. Here's an example of a common acid, hydrochloric acid. It reacts with water, giving us H3O plus and Cl minus ions. Another way to write this is just HCl aqueous. The aqueous means surrounded by water molecules. H plus and Cl minus. We saw the H plus surrounded by water molecules in that picture a couple slides back. Now, a base is a molecule that increases the concentration of OH minus in solution. Sodium hydroxide is a common base. It dissociates into sodium ion and hydroxide. This is the Arrhenius definition of a base. Acids can also be considered as strong acids or weak acids. Same for bases, strong and weak bases. These words have specific meanings when we are describing acids and bases. A strong acid dissociates completely into its component ions. A weak acid exists in its molecular form together and the ions as well. Be careful not to confuse acid concentration with strength. There are some weak acids that are very dangerous. If you're a fan of Breaking Bad, they often use hydrofluoric acid. That is a weak acid, and it's still very dangerous. Hydrochloric acid, HCl, is an example of a strong acid. We've seen this reaction before. There is no molecular HCl in the solution. It completely breaks up into H3O plus and Cl minus. A strong base breaks up completely into its component ions. We will see no aqueous sodium hydroxide, just the sodium ions and the hydroxide ions. Hydrofluoric acid, the picture a couple slides back, that's an example of a weak acid. When it reacts with water, we see H plus or hydronium ion, H3O plus. We see F minus, but we also see the molecule HF existing in solution. There's a double arrow in this reaction, and this tells us that both reactants and products are present. We'll see this more when we get to chemical equilibrium. The same is true for a weak base. Ammonia is a weak base. It will exist in water in its molecular form, also in the form where it has accepted a proton and released OH minus. Here's a list of the strong acids and strong bases. There are 6 listed in your textbook: perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. It will give you great benefit to memorize these acids. The reason is, if you know what the 6 strong acids are, any other acid is considered a weak acid. The weak acids don't completely dissociate. Strong bases are group 1 or group 2 metals combined with hydroxide. The Bronsted-Lowry definition of acid is close to Arrhenius. Arrhenius is the protons concentration increasing. Bronsted-Lowry involves a chemical reaction. In this reaction, nitric acid donates a proton to ammonia. For the Bronsted-Lowry definition, HNO3 is the acid. It gives up the H plus. NH3 ammonia is the base. So the reactant that donates the proton is the acid. The reactant that accepts a proton is the base. According to the Bronsted definition, an acid is a proton donor, a base a proton acceptor. Let's consider water. Is it an acid or a base? In this reaction, phosphoric acid donates a proton to water. We've seen many examples where water acts as a base. Water actually is what we call an amphiprotic molecule. Amphiprotic or amphoteric can act as either an acid or a base. Are there situations where water acts as an acid? You bet. It just depends on if water is in solution with an acid or if it's in solution with a base. Here's a reaction where water donates an H plus to ammonia, so water is acting like an acid, whereas before we saw water acting like a base. So if you are asked, is water an acid or a base? The answer is, it depends. In this lesson, we talked about acid and base definitions, strong and weak acids. We also talked about the acid-base behavior of water. So be sure to work a lot of problems in this chapter. Practice makes perfect. And contact Corey or myself if you have any questions. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.